Okay. Good afternoon. Hello. Hi. Hey. Trying. You want to try something?
Go ahead.
Sure. All right. So hello. As I think everyone knows, the midterms are graded. They're in boxes, and it's really not. It's a misnomer. It's not really a midterm. It's a third term because there's two more, which is potentially good news because that means they're actually each worth less points, and they're each worth 20% of the final course grade. And so here's kind of the grade distribution for midterm one. And so you'll see that really the average grade was in the upper 70s, and really a lot of people landed around that average, I'd say. That's actually, that may strike you, I mean, I think some people may be surprised at their grade, but actually this is pretty consistent for where we land on average with midterm one for this course. And this is probably our hardest exam. And I think that, and given that there's 80% of your course grade ahead of you, I think it means that even if you got a grade that you weren't as satisfied with, there's lots of opportunities to change that in the future. So the answer key is online, and we ask that before approaching us about grading questions or issues, just spend a moment, look at the exam, look at the key, internalize what's going on, and then if you still feel like there's an issue, scan and email it to us. That helps us process it in an orderly fashion. If you are concerned about anything, how anything was graded. We also ask that people that are on the low end of the spectrum, if you got below a 60, to email one of the two of us to talk about options, what went wrong, how we can be helpful,
And to meet with us by a week from Friday so we can diagnose whatever the issue was.
Yep. So that's the data. Then we have the fun part. You're going to the fun part?
Well, before we do that, let me just say, one of the things I'm concerned about in terms of the people that didn't do that great, and there are several of you, particularly the ones in the 70s or lower than that. Why did that happen? Okay. Well, I don't know why that happened. I mean, there are all sorts of different things that you do to work on the material in the course. I mean, one thing might have been that you had trouble with some of the material, but some of it had to do with whether or not you were prepared for the exam. Like one thing I had done on the Tuesday before the exam, I asked a question about how many had worked on the practice exam, and hardly anybody raised their hand. And you had several days to work on that. Now, I don't know. To me, it was very important to work on that exam. That would have helped you prepare for this exam. And to do that enough in time so that you had had that practice. And if you didn't do that, that might have affected it. Of course, other things have to do with whether you're doing the homework relatively on time. And I don't know what else. But, I mean, again, our goal is not to make you suffer. We're trying to teach you this material. We think it's important material. And we want to do our best to have you learn the material, and we give an exam to try to evaluate that, and that's what we're trying to do. Okay, so anything else you want to say? You want to add to that?
Just we're here to help. So I think if you do have any questions about the material, we have some. We try to make available a lot of supports through office hours. We're available on email. We want you to succeed, because we like you.
We do?
Yeah.
No. Okay, now, the next thing I want to do is just take a few minutes just to talk about the very end of the exam. There was the last page of the exam. What was on the last page? The recipes, right? So I want to talk a little bit about what you turned in. And for the most part, what you turned in wasn't that funny, as you could imagine.
We still like you.
We still like you.
We still like you.
And we did our best to try to look through it, look through all the things, and pick out a few things that we'll read to you, and let you judge what you think was the best of the best, or the best of the worst. I'm not sure what the best way to say that is. And then we have a prize for the one that is the best of the best of the best, or the best of the worst. Okay, so I'm going to read a few. Okay, so you think about this, and then we'll let you vote. Okay. First one is for a spicy vegetable soup. 3 tablespoons of sarcasm. Oven baked at 370 Fahrenheit for 15 minutes. 2 cut up models, linear or logistic, not pretty people. A lock of Dean Curran's hair, approximately 100 strands. Spinach, approximately 10 ounces, cut up celery, 3 stalks. Mix it all up in a giant cauldron whilst chanting Donald Trump quotes. Lightly simmer for 10 minutes and voila, enjoy. That's one. Did you like that? I don't know. It's one of the best. Okay. Okay, here's another one. Steps. 1, based on the literature available, determine a reasonable set of ingredients to include in your soup. Sounds like modeling strategy. 2, determine via statistical testing which ingredients may interact to produce a rancid flavor. The preferred method for this is to test several ingredients in a chunk by sampling them simultaneously, followed by eliminating them one by one. Once you have eliminated those ingredients, subjectively evaluate the remaining ones for confounding of flavor. A recommended meter is a 10% change in deliciousness. Finally, do a precision assessment to determine whether you have the remaining ingredients in the correct amount. Throw everything you have left into a crock pot for about 3 hours or until you are hungry again, since you consumed most of your fridge during doing interaction and confounding assessments. That's number 2. Okay. You like that one a little better, I don't know. Okay. Next one, gold standard EVW soup, but the V stands for veggie soup recipe. Ingredient specification, all veggies available from Kroger, broth made with running water found on Mars. Interaction directions, mix both ingredients and remember to maintain significant interaction between the soup pot and a stove. Keep all lower order veggies in the pot no matter what. Assess which veggies confound the tolerable flavor and remove. Compare the widths of the French cut string beans and remove the long ones. You are done. Please do not eat or serve the soup to others. Number 3. I don't have that much more. Another one. 2 diced carrots, 1 diced yellow onion, 3 diced stalks of celery, 3 insignificant interaction terms, 2 of Kleinbaum's loudest 70s shirts, sleeves removed. Did it say 70s?
Yeah.
Oh, well,
yep.
70s.
Sleeves removed.
1/4 of a cup of sweat dripping from my head during this nightmare of exam. Bring to boil, simmer from 4 to 9 p.m., stir with Dr. K's flute. Like that one.
I think we got a winner.
We may have a winner there. Take 1 CNR auditorium and add stressed epi students and exams at a 1-to-1 ratio. Stir for 5 hours. Open the brain of each student. Soup. Okay. What's that? Yeah, I don't know. It was not vegetarian. Okay. Last one. Start second year at Rollins. Add epi and bios prior to starting classes. Cook yourself in
can't read that word.
Medium heat of Atlanta for a few weeks. Then slowly add R programming and epigenetics. By the end of the semester, you are guaranteed to become a vegetable in a vegetative state that you may no longer need soup. It will not help. Okay? So, what are we going to do? We got to vote for these.
I think the flute one seemed to...
Which one do you like?
No sleeves.
No sleeves. How many vote for the no sleeves? Raise your hand, or yell, or say something. You know. Okay. Let's see. Anything else? Anything else that you differed on? The similar with Dr. K's flute. That's the one with no sleeves.
There's the no sleeves one.
Okay, that's the one. That's the winner. That's the winner. And the winner, I don't know who it is. So
you get what's in the bag.
ID is 2145740. Who is that? Come up and take a bow. It's Valerie, right?
Okay. Excellent.
Okay.
Just to reach in. I mean, just to reach.
You have to reach in.
Yeah.
Okay.
Real vegetables, most of which were grown in our garden. Okay.
Thank you. Well done.
Okay.
Excellent.
Now back to work.
Yeah, I know. It's the non-fun part. So all right. So now we got to do the serious stuff again. So we're in this interesting part of the course where we've kind of done the logistic regression thing into its completion and model selection, model building, and we've done kind of these two extra forms of logistic regression, polynomous and ordinal. And we're going to get to another model type, which is survival analysis, in a few weeks. But before we do that, we're going to kind of do this little intermediate zone, which is kind of like special topics in logistic regression, where we're going to talk about a few handy other things that come up that are that you need to know in addition to just the steps of building a nice model. See, for sure. And so we're going to talk about Goodnessoffit and model discrimination today, which really get at kind of, okay, is it a good model in some other sense of good? You know, and I'll explain what I mean by that. And we're going to talk about some diagnostic issues, how to detect problems. We're going to spend only a little bit of time on that, mostly because it's not really different from what was talked about in the second BIOS course. And then we're going to talk about another side topic, which is using the logistic model to get the risk ratio, which more and more is becoming possible and reasonable for many study situations. And we don't necessarily need to use odds ratios, which are maybe favored for more historical reasons outside of the case control study. So we're going to talk about Goodnessoffit and ROC curves today. We probably won't finish it. It's kind of dense, and so I'm going to try to slow down, talk through pieces if you have questions. I'm here for you. We're here for you. And so especially the Goodnessoffit material is a little denser, perhaps, than the ROC stuff. It's a little front-heavy on notation and concepts before we get into something that feels more tangible, but there's just like a lot of notation to unload up front, so we all know what's going on. And so when we talk about Goodnessoffit, we're not talking, is this thing significant? Is this a significant factor? Is it associated with the outcome significantly? Or these kind of small questions that we had inside of the model about specific terms and specific things in the model that we were assessing. We're talking about really a general sense of, is this a good model for describing how the data behaves? And really a global sense. Are all of the things in this model collectively good at describing the data? That's what we mean by Goodnessoffit. Okay, so it's a different question than it is alcohol associated with John Henryism or whatever specific micro question you've got. And so this is really the difference between those is that you might have a significant result inside of your model. You may have a statistically significant result, but the model may just kind of stink in terms of predicting the probabilities of the event and of the outcome in the world. It may not be a very good model, even if you have a significant effect or two. And I'm going to get into the notation more on the next slide, but what I mean by fit, in order to have a good fit, we mean really that, for every observation I, which would be, let's say, person 26, we would like this thing y hat I, which is what the model predicts about the person, to kind of match yi, the actual observed data on the person, right? Ideally, you'd love a model that more on the average, in some sense, or more, in some big way, was able to actually predict back to you the responses on the people that you measured. Imagine if your model, you measured 10 covariates and an outcome. What if it was able to actually predict that outcome really well on average, for the respondents in your data set? That's what we mean by good fit. So, if if we have good fit, this difference should be 0 on average, right? More or less, the model hits the observed data on average, and the difference between the two, the divergence between the two, would be 0. That is, the deviation between the observed and the expected from the model is 0. And so, good fit is, this is kind of we set this up in a way that we've seen before, where the null hypothesis is that it's a little backwards here. The good fit is that lack of evidence of bad fit is the way we're going to kind of formulate our hypotheses. And basically, we're going to have a lack of fit as evidence of bad fit. So we're going to reject a null hypothesis. The null hypothesis is going to be the model fits. And if we reject a null hypothesis through several tests that we're going to talk about, it's going to be that there's bad fit. So the null hypothesis is the model fits well, and we're going to reject that when there's bad fit. So this is, sorry, it's a little wordy here. And so we'll see that in general, and this came up in linear regression when looking at R squared in linear regression, that as you add more predictors to your model, generally your fit gets better. Right? The more stuff you throw in the model, on average, you're able to predict better. The question is whether you want to have a model with 50 or 100 terms in it, and whether that's a wieldy, useful thing, and whether the extra terms that you're adding are really getting you much of interest. But there's this general pattern in regression models that the more terms you add, the more things in there, yes, you're going to predict better. But that comes at costs. So in general, what we're trying to do is have the data be, we're like a model that predicts close to the observed data. That's what we mean by good fit. So we're going to talk about kind of 3 approaches to doing this. The Goodnessoffit tests inside of logistic regression. There's 3 types, and then they broadly break into 2 types. So there's the deviance-based approaches and the Hosmer-Lemaitre test. We're going to talk about the deviance approach based on the saturated model, which is this ideally would be great, but isn't actually possible. So we're going to talk about the next best thing, which is a deviance test based on the fully parameterized model. And I'll talk about what I mean by all this. And so it's valid unless something happens, which we'll talk about, in which case we're going to say use the Hosmer-Lemaitre test, which is more of a universal test that works under more circumstances. And so, we're going to kind of step through this. In order to understand this middle one, we have to understand the ideal situation that you can actually do. So I'm going to spend some time talking about something you can't do, and then I'm going to say, aha, but here's something you can do. So just giving you the roadmap here. So we're going to talk about all 3 of these today on Goodnessoffit. And so here's the notation part. I said there's going to be some kind of, annoying notation here. So I'm going to talk about y sub I, and this thing, little p hat sub x sub I, y hat I, and then the p hat x of I. Okay, so we've seen some of these before, and I'm going to kind of just walk through them. But the difference between some of these methods is in how we think of these, is going to involve these notation. So let's say, here, let's start over here on the right. Here's a 2x2 table. Exposure, disease. It's got 20 people in it. And here we have 6 exposed and diseased, 6 unexposed and undiseased, and so forth. This is kind of a summary view of that data. Okay, so here's 20 folks in a 2x2 table. Down here, I'll talk about what this p hat over here means, but this is a data kind of representation of somebody in this table. So here's a table summarizing 20 folks, but in SAS, you would see 20 lines of somebody that might look like this: diseased, and then this is disease and exposure status. So 2 views of this same kind of data. So the YIs are the actual data themselves, right? So I'm person number 18, I'm Y sub 18, and I'm undiseased, D equals 0. Okay, so that would be Y sub 18. Actual, real data in your data set. That's the Y sub I. Okay, so that could appear over here. I said I was diseased, maybe I'm over here. I didn't say anything about exposure, but let's say I'm over here. And that in the data, we're talking about this column right here. This is the column of the YIs. Okay, so what's this next thing? Well, this is I would read this as the average, this is the average values of Y in your data at patterns of our covariates. That's what it says here. This is p hat sub x sub I. And what this basically means, this is the average probability of the event in your data at covariate x. We're going to talk about covariate patterns in a little bit. But let me go over here to the 2x2 table. In this table, at the value of x, exposure equals 1, so exposure is an x variable. The predicted probability that you might say, or the average probability that you might say just looking at this data, would be that here in this group, in the exposed group, 6 over 10 got the disease. Okay, so 0.6 is our predicted probability, our average, or observed kind of average probability from this data of the disease is 0.6, whereas in this column it's 0.4, right? 4 over 10. I'm not showing the over 10 here. That's the probability of disease in the data at these values of the covariates. So the YIs are the numerator, the actual things that have happened, and these values are the probability. So it's the numerators. It's the sum of all of the disease events over a denominator in that X group. So the number, so 0.6 is the 6 over 10. It's the risk. It's the observed risk, you can say, in this situation where you have binary data. I'm not using the word risk because this could be a cross-sectional study or something else. So at values of our covariates, it's the average values of the zeros and ones, is another way to think of it, right? 0.6 is the average Y experience of the exposed. There's some zeros, there's some ones. On average, it's 0.6. It's the average experience of these folks. Okay, so that's another quantity to keep in mind. So you can look at the actual disease itself, the zeros and the ones, and you can look at the average zeros and the ones, which is here it's 0.6. 0.4. And then we already introduced this on the previous slide. Y hat sub I is the predicted value of the outcome from some model. Any model. Could be a logistic model. So for example, here, and I'll put it down here because this is going to be the same thing. In a logistic model, the predicted values of Y come out as probabilities. Remember, we've talked about this, that in the logistic model, we don't actually quite get these per se. We get this quantity, which is the predicted probabilities of the outcome given the covariates, given somebody's covariates, right? So this is our logistic regression formula, let's say, from earlier. Right? This is the P of X notation. There's the logit form, and then there's this other form of the logistic model. And you throw your variables in here, you turn the crank, and out comes a probability. That probability is the predicted probability, the predicted value, the predicted probability of having the outcome y given that person's covariates. And so here, this 0.41 and this 0.81 is based on this data set, what the alpha and the beta estimate would be. You can use this estimated logistic function, and you can compute this thing called p hat, which is over here. I put the little values over here. 0.6, 0.6, 0.4, so forth. So these look a lot like this. This was not done with the model. This was saying in the data, I just looked at the data and I computed these. I could fit a logistic regression model, and lo and behold, it may come out with values that look quite similar. But the concept of this quantity, this little p xi, is what's in the data versus what a model predicts based on some covariates. That's this bottom one over here. So there's a pattern to this. This is observed, predicted, predicted. The logistic model really does not spit out 0 and 1. So this thing is a theoretical quantity, the y hat sub i's. The model does not actually give you 0s and 1s for people, predicted values of 0s and 1s. It actually only gives you predicted probabilities, this thing on the bottom. But this quantity would be kind of cool to have, this y hat sub I thing for a logistic model. It doesn't actually give that to you. It gives you probabilities. But these are 4 different quantities that we need to talk about. So I spent a lot of time on this slide. Do people feel okay with some of the distinctions between these? Observed, actual, 0s, 1s versus probabilities. And observed versus model predicted, I meant to say. Observed versus model. Questions? Okay. So now we're going to talk about something called the saturated model. This is, okay, we're going to talk about it as this theoretically great thing called the saturated model. And it's so great because it's a model that actually perfectly predicts the data. Okay? And it's a model which, by definition, more or less, is a model where the quantity, this difference is 0 at every observation. So this is the observed minus kind of the predicted y is always 0. Okay, it's a model that is wonderful and perfectly predicts your data, except it's not quite wonderful, and as we'll talk about. So again, so from a logistic regression model, in theory, it would be this model that could somehow give you y hat sub I for every observation, which we talked about doesn't quite give you. But it would be a model where effectively the probabilities that it gave you were always 0 and 1, which is kind of weird, because usually probabilities are between 0 and 1. But it would be a model where the predicted probabilities actually match the observed observations. You told it, I have a person like this, 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 and it spit back to you, they are going to die, or they are going to live, or whatever. It's this magic 8-ball that knows exactly what is going to happen because it predicts every observation perfectly. This is different than, so that would be matching, that would say that the difference of y hat minus y hat sub I is 0. That's different in a sense than saying a model where it exactly predicts the probability of being a case given the covariate pattern. So what if it said, a model that says you're exposed, you have a 0.6 chance of dying, or whatever, and that exactly matched the 0.6 that you found in the population. It's not predicting the average, probability in the population. It's predicting for a given person their fate. So that's, okay, it's a different piece. This is a different idea, predicting the average fate versus predicting the fate of a given person. And so a saturated model actually can always be constructed as a model that has the same number of terms as subjects in the data set. And so one way so you could do this several ways. One way would be to have a no-intercept model that has a dummy variable for every single subject. Okay, it's not a very useful model, but you can imagine there's this model that you can make that would have we're using these little Greek letters here to represent the beta terms, but this could be beta 1 times z1 and so forth. And this is an indicator variable for whether somebody is subject, ID 22 or whatever. Every person has their own special term in the model. And you can imagine that these betas would basically return a 0 or 1 on average for a given person. Okay, this is your person 22, you're gonna live. So this coefficient will translate to 0 or 1 predicted probability. You can basically include a term for every person in the model and basically construct this perfect magic 8-ball that would predict the outcome for every single person. That would be possible. And so, for example, if somebody was person 2, let's say I'm person 2, so my indicator variable is z2 is 1 and everything else is 0. Then for me, the model reduces to a single term, and this is in the logit form, and then this is in the probability form, and it's going to always this is always by definition the probability, the predicted probability of the outcome given I'm person 2. But in this special case, it's going to actually always equal the observed data, or this is going to equal the yi actually observed for person 2. It's going to always, if I have a term for every person in the model, I'm going to get a 0 or 1 out of the model for every single person because it's saturated. It is saturated. We say saturated. It has a term for every unit of data. Every observation has a term. So it's called a saturated model. And by definition, if everyone gets their own special coefficient, it's going to be able to exactly connect the dots, as it were, of every person in your data set and exactly predict their outcome. So if this was linear regression and you had a cloud of data points on an x by y plot, this would be like fitting a function that connected every dot. That's why I said connect the dots. It would be like having a beta term that would exactly put you through every dot on your plot. And this is the logistic regression equivalent. If I had a term for everyone in the model, I would always predict what happens to them. This is not very useful. This is not the best model. You didn't do your study to include terms for the people. You did it for abstract concepts, right? I measured alcohol, I measured smoking status, I measured things about the people. Putting the actual indicator variables for the people in your data sets is probably not very generalizable, right? You're not trying to make a model. The model of your 100 people is not something you want to generalize from, or is not a generalizable thing. And this on the bottom here is showing how the likelihood, which we talked about this quantity of the probability, it's a probability measure of how likely your model fits your data, or the probability of the data given your model, more precisely. And so here, the likelihood is always equal to 1, which basically, and we'll see this again in a little bit, this basically means this perfectly fits your data. It doesn't get any better than this. All the coefficients exactly match your data. And so this is the saturated model. It's a model in which you have a term for everyone, but not very useful. And so here's an example where we have now we have two 2x2 tables, because I've introduced a covariate c equals 0 and c equals 1. So we have this extra, we don't just have disease and exposure, but we have also c equals 0 and 1. And so now we have 40 people. Okay, there's 20 people in this table, 20 people in this table. So this model, I'm going to fit a model that doesn't think about E and C and actual kind of not actual things that you might want to put in the model. Instead, I'm going to fit a really weird model, and it's going to be model D equals ID. And why am I doing that? Well, if you say class ID, model D equals ID, what it's going to do is make dummy variables for every single, if I have ID 1 through 40 in the data set, rows 1 through 40, it's going to fit a model with 40 terms in it. Okay, so this is like a kind of a dumb model. You wouldn't actually want to do this. But this is a model that effectively is going to fit a saturated model, because it's going to have 40 terms, especially because I'm going to say no int. That means no intercept. And it's going to give me, it's going to use all, if I have 40 people, it's going to fit 40 terms, no intercept term. And I'm going to fit this model. and I'm asking for some extra output. I'm going to ask for this p equals p hat. So this is going to be, this is going to be, this output line, do people know the output command in statistical procs, right? This is, this basically is, hey SAS, give me a data set of results that are about each, that correspond to each line of data. So if I want predicted probabilities or model diagnostics on each row of data, I use the output command. And so what I'm going to say is this is going to make a data set called pred. This is the data set name. And it says make a column. I'll make a column called p hat and store that this p is this together is telling it to give me the predicted probabilities, okay, and put it in a variable called p hat. And basically what you see is this is the data set. This is a print of pred, the data set pred. And what you see is here's a person who is exposed, and the y sub I, their predicted, or their actual observed disease status is 1. The model says 0.99990. And then for everyone who's diseased, it's going to say that. And for the undiseased folks, it says 0.00001. Basically 0, 1. Right? There's some rounding or some other funky things here, but basically it's predicting exactly people's observed values. Okay, so again, this is not a very useful model, but in a sense, this model is as good as it gets. This model is awesome prediction. I would love a model. What if you had a model what if exposure and the C variable described a lot of the disease process? What if those two variables, if you knew those two things, you pretty much can describe the data really well? Then you might imagine if you fit a model with E and C in it, that maybe you'd get p hats that are pretty close to 0.999 and 0.001. It was really good at just getting close to the observed zeros and ones. Okay, that's kind of the idea of Goodnessoffit. This is an idealized model that doesn't actually make sense. But what if the p hats in your other model, on average, were similar to the p hats in this model? It's kind of the intuition that we're going for. Notice if you ask for this option, lack fit, it gives you some other interesting things, which we're going to talk about more, which is going to give you one table called the model fit statistics, and it's going to give you this thing called the deviance Goodnessoffit statistics, and notice these values are basically 0. That's going to be important. This represents the deviance from a saturated model. It's basically 0. So the idea here, I showed you a model that's kind of dumb because it has 40 terms in it, 1 for each person in the data. It perfectly predicts the observed values, but it's not. So the model fit really great, but it comes at a cost because the model's not a good model. The model's not usable. It's not useful. It's not generalizable. It wasn't good. So can we fit a model? We know the saturated model stinks, but what is our model close enough to a saturated model? Can we find a model, can we fit a model that's actually functionally close to a saturated model? Can it almost fit the data perfectly? And how close is almost? How close is close enough? We're going to basically formulate the idea of a likelihood ratio test to model. Is our model close enough to a saturated model in terms of its performance? The saturated model stinks. Can we find another one that performs almost as good at predicting the data? That's kind of the idea. And so there's this. So this sounds like a likelihood ratio test, and this idea is formalized in a quantity called the deviance, which is another. It's a manipulation, effectively, of likelihoods, and it's defined as above as the -2 times the likelihood of this ratio. The numerator is the likelihood of the model under consideration. And the denominator I'm going to call L max, okay, which is the likelihood of the best fitting model. In our case right now, we're talking about the saturated model as this ideal model we would love to compare things to. Okay, so this quantity called the deviance is going to measure how close our model is to the idealized best model of the saturated model. And the idea is the smaller it deviates, i.e. deviance, the less our model deviates from this ideal model, the better the data fit, or the better the model fits the data. But the question is, where do we get, what is Lmax? And right now I've been talking about it as if it's this thing from the saturated model, and we're going to talk about where it's not going to work out. But what if we could compare our model in the numerator over the saturated model, which we're going to also call the subject-specific model, right? It fits a term for every subject. And this, in the model that's in the saturated model, the outcome is perfectly predicted for each subject, okay? In this situation, the likelihood is equal to 1. It's always equal to 1. That was, I showed the algebra for that on a few slides earlier. Algebraically, the likelihood always is 1 in that model. There's going to be an alternative ideal Lmax model called the events trials model, or events trials model, events trials deviance, really, or likelihood. And it's going to be from not the saturated model, but something called the fully parameterized model. And it's not quite perfectly predicting as a saturated model, and we'll talk about what it is. It predicts the probability of the event on average rather than the event. I'll talk about that distinction. So we're just going to talk about this one. We're going to conclude this stinks. Remember I said where there's going to be 3 things. I'm going to show you the first one is ideal but doesn't work out. This is the one that's going to work out, the events trials based formulation of the deviance. So the big picture is we want to compare the likelihood of our model to some comparison model that we think fits the data really, really well. And we're going to test how far off we are. This basically is that this shows that this is the same as the likelihood ratio test, more or less. The likelihood ratio test was a test that we have seen before, where we're comparing kind of a full and a reduced model, right? And we're testing for statistical significance of factors dropped. We've talked about that before. You can rewrite this quantity of this thing called the deviance can be used to conduct a likelihood ratio test if the two models that you're comparing are nested, right? One has fewer covariates than the other, and it's the same covariate. So you have a full model, you dropped a few things, you reduced it, and now the reduced model is nested inside of the other. You can just, if you follow through the algebra here, you realize that if you look at the difference between these two, if you have the deviance of one model and the deviance of another, you take the difference of them, and it's actually the same thing as the likelihood ratio statistic. Okay, so this is conceptually almost the same thing. The deviance is specific, is a little more general because we are not necessarily talking about nested models. As we'll see. So just putting this up here because it's really, there's similar concepts, and I want to draw that connection to the likelihood ratio test. So the problem is that we really can't use this thing called the saturated model and its likelihood in a Goodnessoffit test. So ideally, we'd love to compare our model to a saturated, perfectly predicting model. Using this likelihood from the saturated model for the denominator, that thing called Lmax. The problem is we can't, because if you remember, the likelihood is always equal to 1. This denominator piece is always equal to 1 because the model is perfect. And when we do that, it drops out of this fraction effectively when the denominator is 1. And the deviance quantity is just equal to is basically just equal to the likelihood, the negative 2 log likelihood of the model that is our model of interest that we're comparing to the saturated model. So basically, this denominator thing goes away, and we're just stuck with a single likelihood. So we're not actually comparing anything. If you imagine you're always dividing by 1, you're not actually comparing to anything. So sorry here. So so basically this is problematic. It goes away. We can't really. This is just not a very helpful quantity. It always drops out of the denominator. This denominator piece this thing is called the subject-specific deviance, is another way to talk about it. And it's just not a helpful quantity. We can't actually use it because it's always equal to 1, is basically the sum of it here. So it would make sense. It would be great to compare to the saturated model, but we can't. So what are we going to, we're going to have to move on here. So the specific problems of using this statistic without the denominator is that this deviance, what we're left with, only uses the predicted probabilities from our current model and makes no comparison to the observed values. And this thing is not distributed chi-square or usefully in any way, so we can't actually conduct a statistical test for it. And this is just not usable for Goodnessoffit testing. So the saturated model is great, can't use it. I've said that 100 times, but that's where we're at. So this is several slides to enforce that. But we have an alternative. We have this thing called the fully parameterized model. Okay, and so it's a variation on the idea of what it means to be perfectly predicting the data. So the saturated model was this weird model that always spit out zeros and ones as its probabilities, which is not actually what a logistic regression model is supposed to even do. But it basically spits out zeros and ones that fits. Therefore, this difference is effectively 0 always. So, okay. But imagine another model called the fully parameterized model that doesn't have a term for every person. It has a term for every combination of predictor variables. Okay, so imagine if you had E and C. You only went out in the world and measured E and C on your respondents, your participants. Then the fully parameterized model of E and C, if that's the only two things you measured in your whole study, would be a model that had E, C, and the interaction, the product term between E and C. So this is like saturated on the covariates. It's got as many covariates as you can throw in there of data that you actually measured, not dummy variables for the people, which is what the saturated model was, but this is the stuff you actually measured in your study. So the fully parameterized model is the best, most covariate-filled model you can make. Okay, so this is another ideal, right? What's the best model you can make out of the data you've met, out of the things you've measured? Well, it's this one. In some sense, this is the one that can predict the most. Now, functionally, this may not be, if you measure 10 things in your study, this is going to be a really big, clunky model also, right? This is not going to, the fully parameterized model, when you have 10 things or 100 things that you've measured in your study, is going to have a lot of terms and all the interaction terms up to the 10-way interaction, the 10-way product term. It's going to be all the ways you can pair up all of the covariates. So it, too, is not a very good model in terms of functionally something you'd ever want to use, but it's another ideal for predicting the most stuff. It's not necessarily going to be a saturated model at all. This is probably going to have way fewer terms for most studies than the saturated model, which is always the number of predictors is the number of observations. This is the number of combinations of all the things you've measured. So in this case, the fully parameterized model has only 3 terms, not 7 or 4 with the intercept. If you only measured one thing in your whole study, then the fully parameterized model has just a single term. This is the best model you can make from the data you've gathered. So this model, what's neat about the fully parameterized model is it doesn't predict the 0-1 responses perfectly. It predicts the observed probabilities on the average probabilities at the covariate patterns on average. So it doesn't hit, I'm going to go all the way back here, sorry. I'm going to go back to this slide. It doesn't predict the 0s and 1s. It predicts the 0.6s and the 0.4s. It predicts the probability of the outcome at a given set of covariates. So it's actually very, very good at predicting the average experience. And it's something that maybe makes a little more sense than the saturated model, because it's actually using the data that you got. So in order to fully appreciate how that works, we have to talk about this thing called covariate patterns, something that SAS calls unique profiles. And it's all of the observed combinations of the covariates in your data. Okay, so for example, if let's say, here's some examples. If you have a single 0-1 predictor exposure, then there's only 2 covariate patterns possible. You can have people that are exposed and people that are unexposed. If you have 2 binary predictors, let's say E and C, then you have 4 possible covariate patterns, like 1, 0, 0, 1, 1, 1, 0, 0. Okay, when you have these kind of categorical predictors, you can always kind of define all of the unique intersections of the covariates. Those are called covariate patterns. And the cool thing with this, like I just said about the fully parameterized model, is that at a given covariate pattern, it predicts the probability perfectly, the average probability of disease perfectly. And so at every given one of these, it will predict that the probability is 0.6, 0.4, or whatever. So covariate patterns, when you have categorical data like this, categorical predictors, or you can kind of enumerate them. When you have, let's say a single continuous variable age, then the number of covariate, let's say, you had a continuous age from 18 to 100, then the number of covariate patterns, if you had just age in the model, is going to be basically, it's going to be as many distinct values of 18 to 100 that you observe in your data set. It's going to be a defined number. It's going to be kind of, you can enumerate that, pretty reasonably. It's not going to be too crazy. But what happens is when you have continuous variables or multiple continuous variables and categorical variables together measured in your data, you can have many combinations of all of these covariates observed. You can have a large number of covariate patterns. An 18-year-old who was exposed and exposed this to this, but not exposed to that. But that's different than a 22-year-old with the same categorical E and C variables. So generally, the covariate pattern stays rather small when you have categorical variables, but when you have continuous variables, that blows up the number of combinations of X variables that you see. This is going to be important in a moment, this whole concept of covariate patterns. So we use a notation called G to represent the number of unique covariate patterns. So in here we have, if a single binary exposure, it's just going to be G. There's only 2 covariate patterns. G is 2. Here, G is 4. If you have age, a continuous values of age, G is likely large. You have a whole range of ages observed. You're going to have many different covariate patterns. If you have age and a binary exposure, you can have even more covariate patterns. And so we're going to use this quantity G. So we're going to name this G. Usually when you have, G is going to be pretty small relative to the sample size when you have categorical variables, but closer to N, the number of observations when you have continuous. You may have as many covariate patterns as people in your data. Everyone's different. No 2 people are the same. Everyone's got different combinations of your X variables. So, we've already talked about this. Basically, when you have a single predictor, G is 2. If you have 2 binaries, it can be 4, and it can get much more complicated. Okay, so let's actually bring this back to Goodnessoffit and analyses and why we're here today. So, given we have a model here, we're going to talk about how to think about fully parameterized model. We're going to use the fully parameterized model to conduct a Goodnessoffit test. So let's say you have some predictors, X1, X2, or E and C, and so forth. We're going to make a fully parameterized model, and it's going to always have an intercept, and G-1 predictor is defined from basically all that's going to hit all of the covariate patterns. And so what I mean by that is this. It's going to be, if we have 4 levels of E and C, we're going to have a model with 4 terms in it that's going to perfectly model E and these 4 covariate patterns on average. That's going to be the model with an intercept, E, C, and E by C interaction. That's going to be 4 terms in your model. Intercept, E, C, E by C. And it's going to basically be a model that can perfectly predict what goes on for 4 covariate patterns. It's going to be the fully parameterized model. Okay, so here's one model. Here's the data. Again, and we saw this data earlier. 2 2x2 tables with C equals 0, C equals 1. Here's, I'm going to put it in the, I'm going to use events trials type format. Remember this? This is, we use, I'm using kind of the aggregate. I'm taking the aggregate 2x2 data, and I'm feeding it into SAS. Okay, so I made this data set here. This data set reflects that. And here's the model. Okay, model disease over total equals E, C, E by C. This is the, in a sense, it's the fully parameterized model. Okay, it has an intercept. It's got E, C, and E by C. This is the most data we measured. This is the biggest, most robust model we could even measure, or we could even fit. This is the best model we can make. We did not measure anything else in the data. You can actually argue that maybe this is saturated because there's only 4 lines of data, because I didn't actually put individual IDs in here, but that's more of a philosophical aside. The basic idea is that this is the fully parameterized model. There's nothing, all we have is D, E, and C. We fit a model with E, C, and E by C. This is a fully parameterized model. Okay, so here's some other pieces, here's some other things we might have done on these 2x2 tables. Here's the predicted probabilities, or really the average, based on just observing, on what we've observed in the data. This is what you predict the probabilities of disease were for people who are exposed and have C1, unexposed and have C1. See, these are the risks in each of these 4 groups, basically. 0.6, 0.4, 0.3, and 0.7. Okay, this is just, you don't need logistic regression to tell you these. And these are the odds ratios that you might have observed on those tables. Okay, here, notice SAS will tell you that. This is important. Look what SAS did here. If you had the output line, which we don't have here, but if you had the output line, SAS would say for the people that have E and C are both 1, their predicted probability is 0.6. It's not, okay, that's what it's saying. It's not saying it's 0, it's not saying it's 1. It's predicting that given this data and this model, the predicted probability of an E and a C person is 0.6. If you have E equals 0 and C equals 1, then it's 0.4, so forth. This equals this. Okay, this was computed by hand on the 2x2 tables, and this model is perfectly predicting the average experience of this group. Okay, that is the fully parameterized model. It predicts the average experience of the group. It doesn't predict exactly what what happens to every person. It predicts what the average experience of that covariate pattern. Okay, so these are 4 covariate patterns: the E1, C1s, the 0 ones, the 1 zeros, and the 0 zeros. This model that has all the possible interaction terms predicts the average experience perfectly. Okay, so it took us a while. It took us a lot of notation to get here. But this model is ideal in that it's the best fitting model in terms of the covariates you have. Fits the data perfectly on average. Okay? If you look at the deviance table, it's going to tell you, again, it's deviance. This is going to say deviance is 0, which we'll talk about what that means. And then there's this other thing here. This quantity is the deviance sums of squares. The deviance of the saturated subject-specific model. This is the quantity that we said to actually, we didn't like to use that because the denominator was equal to 1. So we'll talk about we'll talk about that. So this model perfectly predicts the odds ratio that was observed in the data, and it also predicts the risks, the p hat sub i's. It predicted exactly the kind of what was observed in the population perfectly. The model wasn't saturated. It didn't spit out zeros and ones. And this thing called the deviance of the subject-specific deviance was greater than 0, or its likelihood was less than 1. It's not the saturated model. This is something different. The saturated model would have had 40 terms in it. So that's not what this is. But in a sense, this model is maybe better. It has better fit. It predicts the average experience of the population very well. So you can say that instead of y hat so instead of y sub I minus y hat sub I equals 0, it has the model predicted probability minus the population or the sample probability is equal to 0. This minus this is equal to 0. It predicts the average experience perfectly. Okay, so this is the way to formalize that. Okay, so here's another. This slide is the same information. I just did it as 40 lines of data. It's going to show the same thing. This model is not saturated. N is 40. There's 40 observations, but only 4 covariate patterns in the model, 4 things in the model. Okay, here's a different model that I'm going to fit to the same data. This model has no interaction term. Okay, so this is, see, there's no EC. This is the same model as before, but no EC. Okay, this is, imagine you were doing your study, okay, and you wanted to know, you did all of the variable selection, you did all the model selection, you did the whole EBW process, and you got to this model at the end, and you think that EC is a really good model. You say, I think this is the best model because it, I got rid of all of the, I feel confident that all the confounders are controlled for, all the interaction terms, all the EW terms are taken care of. I think based on the ideologic process that we've discussed already, this is the best model. And now I want to know, well, does it have good fit? Does it actually describe the data well? And now we're entering goodness of fit mode. Notice this is not the model that has EC in it. It's just an E by C interaction. It has just E and just C. So now I'm going to ask SAS for the lack fit option, and it's going to give us model fit statistics. And it's going to give us here, notice this says 0. This was 0 over here. This says deviance 0. Now it says deviance 3.6961. This quantity, this value of deviance that it gives us is what we're going to call the events trials deviance, or really the deviance from the fully parameterized model. This quantity is really cool. This is the thing that we're going to use to conduct our goodness of fit test. This tells us how far off our model's likelihood is from the fully parameterized model. Okay, so this is the thing we've been marching towards for the last like 30 minutes, is to get at this quantity here. On the fully parameterized model, the one that had the E by C interaction, this thing was 0, and suddenly it's 3.69. This was 0 previously because this was the departure from itself. This was how far away was this model from the fully parameterized model? Well, this is the fully parameterized model, so the deviance from itself was 0. This statistic is, now it's not 0 because we've dropped a term. We don't have this term in there. We brought SAS this model. We said, I have a model that's D equals E and C. Tell me about its goodness of fit. And it's going to say, well, it deviates from the fully parameterized model by 3.6961. This is degree of freedom 1. This is going to be, we're going to do a chi-square test with this. Okay. So this is the thing that we're going to use. We're not going to use the negative 2 log likelihood deviance from the subject-specific model. We're not going to use this piece that I showed earlier. We're going to use this other deviance statistic. And we're going to use it to conduct a goodness of fit test. It's a chi-square test with degrees of freedom being the number of terms kind of dropped from the fully parameterized model. So it's the number of terms. It's the number of terms that differ from, if you had all the different interactions of all the covariates in your model, it's the number of terms between that fully parameterized model and your model that has 6 terms in it. It's going to be the difference. Luckily, so often that's actually really annoying to compute. SAS is going to tell you. It's going to tell you right here how many degrees of freedom it is. This one was easy. We know that there's just E and C, and so E by C is the only term missing. Therefore, it's 1 degree of freedom. Another way so you can conduct a formal hypothesis test. The null hypothesis is it's a good fit, and when you reject this null hypothesis, you're saying, okay, the alternate is lack of good fit. It's not a good fit, bad model, and so not like bad dog. There's a dog coming up there. There's still a dog, but so. You could do a formal chi-square test, or there's kind of like a rule of thumb inspection type test that says the deviance over the degrees of freedom should be about 1. Okay, so You can do this the kind of the quick and dirty way, which is this should be approximately equal to 1, or you can do a chi-square test. Okay, there's a big caveat to this, which is that you can only do this test when the number of covariate patterns is relatively small to the number of observations in your data set. So here, we had a situation where there's only 4 covariate patterns, the various combinations of E and C equaling 1. So that's 4, and there's 40 observations in the data set. So that's okay. The closer you get to G and N being the same, you basically approach the saturated model. Like, what if you had only 4 rows of data and 4 covariate patterns? Then your fully parameterized model was the saturated model. It's a little deep for something new. But imagine, like, the fewer number of observations you have relative to the number of terms in your model, you get back to the saturated model. So basically, this only works when you have relatively few distinct covariate patterns relative to the data. Otherwise, this kind of all falls apart. When does this happen? This happens generally when you have continuous covariates. I have age, I have blood pressure, I have whatever as predictors. I have as many covariate patterns as people in the data set, and everyone's distinct. And when that happens, we can't use this Goodnessoffit test. We're going to have to use something called the Hosmer-Lemeshow test that I'm going to try to run through quickly. It's a much simpler test, conceptually, frankly, than the deviance-based approaches. Okay, so this is the events trials business, the deviance events trials, or the deviance fully parameterized, whatever model approach, and only works generally when you have these kind of few number of covariate patterns, generally with categorical variables. Why was there dogs? This was supposed to be that this is a big dog and this is a little dog, and we want the number of covariate patterns to be small relative to the sample size. So if they were 2 dogs of the same size, we would not want to use the deviance-based approach using the events trials format. Okay, so that's why there's dogs. Somewhere at the beginning of the course, we promised dogs and babies, so we've shown both now. So I'm keeping track. So the Hosmer-Lemeshow test is a more general test of the same idea, that on average, you want the model to basically hit the average predicted probabilities. You don't want it to hit the 0s and 1s exactly. We want it to predict the average experience of the outcome in the data set. It does not involve the deviance, and is better when you have, it's really working at the other end of the spectrum when you have unique covariate patterns. You want to have a large number of covariate patterns, frankly, and ideally, it works on this other end of the spectrum where you have age and all these continuous variables, and you've got problems with using the other test. It does fine. It does fine over here when you have complex covariate patterns. And the basic idea is it's going to look. We're going to look at these. We're going to call them deciles of risk. We're going to divide the data into groups, and what it's going to do is it's going to look at the sum of the predicted probabilities and look at the sum of the observed outcomes, and it's going to compare them. I'll show you what that means, but it's going to compare the grouped experience of the data in some way and say, did the model on average in these groups was the average experience in this group the same as the observed average experience of the group? Was it similar to what the model predicted for the group? Okay, so it's going to be the observed outcomes, and it's going to compare it to what the model predicted. And it's going to be similar to a chi-square test where we've compared observed and expecteds in a number of different ways. So we're going to use a data set called the Evans County data set. And this data set has, it's a cross-sectional study. The outcome is going to be cardiovascular disease, CHD here, 0, 1. And there's an exposure variable, catecholamine, 0, 1, and some other, and notice there's a whole bunch of covariates. In a sense, we're not going to go too far into the example because I'm just going to show you what happens in the Goodnessoffit test. But importantly, it has 2 continuous covariates, age and cholesterol, and then some binary variables. And the idea here is that the combinations of all of these, variables are going to give me many, many covariate patterns, invalidating the other approach. the deviance-based approach. I'm going to want to use another test. Here's a model. Let's say this was your model. You do exactly as we tell you in this course, and you go through the whole process, and you win a gold star, and you've got this as your final model. This is perfect. And now you've said, but does this model actually describe the data well? It's significant. It's statistically significant, but does it actually tell me anything? Does it actually describe the fit of the data? Does it fit the data well? And now you're in Goodnessoffit territory. Here we expect the number of covariate patterns to be about the sample size, given that there's two continuous variables in complex kind of ways here. So this is the output of the Hosmer-Lemma test. And I'll kind of walk through it. And it's really, if you stare at the output of it, it kind of begins to make sense. So it's actually easy to jump to the end here as we walk through it. The first thing it does, it splits the data into tenths, deciles. And it ranks the people based on their deciles of risk. And so what it means by that is it ranks the people by their predicted model probabilities of getting the outcome. Right? So the logistic regression model, right, it gives everybody a quantity p hat xi. Every single person can get a p hat, a predicted probability, and it ranks all the observations. You have an 80% chance, according to the model, of having cardiovascular disease. You have a 62% chance, or whatever it is. It ranks all the observations and then cuts them into tenths. Okay, and that's kind of what we got here. It's cut into tenths here. And so what you can see that kind of look over here. This is what it's doing. So notice this is ascending here. This is the sum of expected probabilities of having cardiovascular disease. These are the deciles of risk here. So here, I'm going to put these two up. This is CHD equals 1. This is the probability of having coronary heart disease, cardiovascular disease. I'm saying CVD. This column is for the 60 people that were in the top 10% predicted risk. The 60 people in that most risky group actually had 29 instances of 29 values of y, and therefore 31 values of 0. This is the actual data. In these 60 people, 29 had the outcome, 31 didn't. Okay? Notice this, they're a pretty high risk group. Half of them effectively had the outcome compared to like the lowest group, 2 and 59, basically. So the sum of their y's, the sum of their zeros and ones, there's 29 ones and 31 zeros. The model, if you look at each person, if you sum up what each of the people was predicted by the model, wow, it's really close. The model, for those 60 people, if you sum across them, came up with almost 29 on the dot predicted cardiac outcome events, and 31 on the other side. So wow, look at this. So you go down here to the decile 3, 2.68 versus 2. That's pretty good. So across those 61, we saw only 2 outcomes, and the model said there should have been 2.7. So notice this is not at the individual level. This is at kind of like the group-wise experience level, which is kind of what the last Goodnessoffit tested. This is about the average experience of the group. Does this feel like good fit? Should feel like good fit. The model, wow, it's nailing. In these 61 people, it said 0.94 and it should have been 2. Should have been 29. It predicted 28.7. So it's actually like a pretty good model. The Hosmer-Lemma test is a formal comparison of these two columns. That's all. It's a chi-square test that is trolling along the rows of this column between these two columns and comparing how far off the model's expected prediction was from reality. Okay, and it's going to use this other side too, but you get this by subtraction. This is really easy to do. You can just subtract it from 60 and 61. So all that the Hosmer-Lemma test does is formalize that intuition of it goes along each of the 10 rows and does observed minus expected squared over expected. So 29 minus 28.71 squared over 28.71. It does it on this part here and on the 0 part over here. And it's, again, same null hypothesis. Good fit is the null hypothesis. So if you fail to reject the null hypothesis, the model seems to fit well. There's no deviation between the observed and the expected. It's pretty good. They're pretty close to each other. And the alternative hypothesis is, whoa, these columns are very far apart, actually. The expecteds and the observed don't line up, right? So, and that is a chi-square with 8 degrees of freedom test. And so here on the Evans County data, what you get here is a Hosmer-Lemeshow test if you use the lack fit option. 0.4343 is the p-value, so you fail to reject goodness of fit. You say, actually, we think this fits the data pretty well. This is a good model. Not only were things significant and odds ratios and all that other stuff we used to care about, by the way, the model also describes the data well. Notice 599 unique profiles, this thing says, underneath the goodness of fit test. This is the G. So there were 599 covariate patterns in the data, and we had only like 600 observations, 9 observations or whatever it was. So 599 ways to have the covariates, and it's almost the same as the sample size. So we needed to use this. We could not have used the deviance-based test. This was a good idea. We're going to go in a second. So this is the formal definition of what we just said with more notation, but it's the same thing. This is the formal way to, tell how do you actually go about computing this. We just kind of listed the steps here. I'll get to this on Thursday. Well, there's like 2 more slides. We'll get to it. We're going to get to the right place. I'll see you Thursday.